Hi everyone, I'm Tulsi Komlo, and I'm happy to give this talk for the Bitcoin Research Prize in collaboration with Jonas Nick. So Frost is work that I worked on with my co-author Ian Goldberg, and Jonas worked on MuSig2 with his co-authors Tim Ruffing and Yannick Surin. And we're happy to jointly receive this Bitcoin Research Prize. So you might be asking, why is there a shared prize between Frost and MuSig2? And so it's kind of interesting that we are sharing this prize. And I'll tell you why using essentially a story in 4 parts. So the first part of the story is when myself and my co-author Ian Goldberg put out this work on Frost, which is a flexible round optimized Schnorr threshold signature in 2020. And so we put this paper out, and much to our surprise, a couple of days later, we got an email from Tim Ruffing and CCing his co-authors. And it was very interesting to read this email because in it, Tim said, hey, this is really interesting work. It actually looks extremely similar to our work on a multi-signature scheme that we called MuSig2. And essentially, this work uses similar techniques to our work on MuSig2. And then this work came out a little bit later, showing exactly that. And so we have 2 papers. One is a threshold signature scheme, one is a multi-signature scheme, but under the hood, they use very similar techniques, which were arrived at completely independently. So that's kind of interesting, the way that science works. But the story has a happy ending. So since that point, we've given a lot of joint talks and done joint work on both of these schemes in conjunction. So this is myself and Tim Ruffing giving a talk on Frost and MuSig2, along with Elizabeth Kreitz, who has done some follow-up work with me on Frost. So overall, interesting story, but it overall has a very happy ending, I think. And so overall, I think the summary from the story is that science is really magical. So the takeaway from me is this. And, you hear about in history how in science and math, ideas sort of emerged independently around similar times. And it was really interesting to be a part of a process where this happened, where literally in the exact same time period, we came up with a new cryptographic technique independently. And so I think that's really cool. And it was also very reassuring that the technique we came up with was natural and also, as we showed later, is secure. So yeah, overall, I think this is a fun and happy story, and this is why we're sharing the Bitcoin Research Prize. So I'm going to start off by discussing some theory. So I'll dive a little bit deeper into what threshold and multi-signatures are. And then I'm going to introduce Frost. And Jonas later is going to introduce MuSig2, and then you can see the differences between these 2 schemes. Okay, so about some theory. So first, I've been referring to this notion of threshold signature schemes. So let's talk really briefly about what that is. So a threshold signature scheme is a T out of N scheme, where T is the threshold and N is the total number of parties. So here I'm showing you a 2 out of 3 example where we have 3 total parties and 2 parties are required to participate in signing. So what we have is we have 3 parties that each hold what we call a secret key share. And then 2 parties are only required to participate in order to issue a signature. And we have 1 public key, which represents the entire group. And so you might say, like, okay, how are these key shares actually generated? And that's done either via a trusted dealer. So 1 party goes and generates all the key material for all other parties, or you can do key generation using a distributed key generation protocol where no party is trusted, but this key material is generated nonetheless. And we'll talk a little bit more about this later. And what's important to note about threshold signatures is that they're secure up to T-1 corruptions. So here, even if one party was corrupted or their secret key share was lost, and the scheme still remains secure, i.e., no party can forge a signature without requiring an honest party to participate. And I just want to re-emphasize that signing here is done without revealing secret key shares to other parties. So essentially, secret key shares stay local to each participant's device, and they're not sent around to other parties. So next, I want to speak really briefly about what multi-signatures are. And what a multi-signature scheme is it's actually a special case of a threshold signature scheme. So a multi-signature scheme is the n out of n setting, where the threshold signature is the t out of n setting. So here, t is equal to n-1 for multi-signatures. And the reason why multi-signatures are useful is because you can do key generation in a non-interactive manner. So basically, every party can generate their keys themselves, and then they can sort of spontaneously come together in order to sign. So yeah, so depending on the use case, you might want a threshold signature or a multi-signature. So I referred to the security of multi-signature schemes at a high level, but just diving in, when I say the security, the first property, what I mean is the notion of unforgeability. So that means that an adversary cannot forge signatures without honest participants also being involved in that signature generation process. And the second notion of security is liveness. And this notion isn't often, it's not talked about as often as enforgeability, but I think it is extremely important to consider. So essentially what liveness means is that the system can create signatures whenever one is requested. So it essentially means that your secret key shares are not bricked. And yeah, so I think we tend to over focus on enforgeability, where liveness is also just as important to consider. But mostly I will also kind of focus on enforgeability for the remainder of this talk, but I do want to stress liveness is important. So a little more formally, when I say enforgeability, what I mean is that we have some adversary, and the adversary can declare which parties are corrupt at the beginning of the game. And then the adversary receives the secret key shares for those corrupted parties. And then it receives public key shares for all parties. And then additionally, the joint public key representing the group. And then, and here I'm just modeling key generation as being done by a trusted party. And then this adversary can participate in assigning protocol representing these corrupted parties. And what it can do is it can query the honest participants to sign messages of its choosing. And we say that an adversary is successful if it's able to output a valid signature on a message which was never queried to an honest party. So this win condition is the same as enforgeability for single party signature schemes. But the difference here is that the adversary is able to interact in the signing protocol, and it receives key shares for corrupt parties. Okay, so now I'm going to briefly remind you what the Schnorr signature scheme is for a single party. So for Schnorr signatures, what you do for just one party is the signer generates their key pair, so some secret key, and then public key, which is just a generator raised to the secret key. And to sign a message, they generate a nonce. They sample it uniformly at random, and then they generate a commitment to that nonce. Then they generate the challenge via fiat shamir. So here they hash the public key, the message, and the commitment. And then the signature is the nonce added together with the challenge and the secret key. And yeah, so then the signature is the commitment and the response. And to verify, the verifier rederives the challenge, and then it essentially checks the relation in the exponent. So it uses the commitment, the public key, and the challenge to check that this relation holds with respect to the response that was output as part of the signature. So yeah, so it's very similar. So this is essentially a discrete log proof of knowledge scheme. So when we want to thresholdize Schnorr signatures or perform Schnorr signatures in a multi-party setting, there's really two main questions that we have to consider. So the first question is how you would share this nonce R among all of the parties. And the second question is how you would share the secret key. And so these two factors really, when you look at different schemes in literature, this is what distinguishes different schemes from each other, is how they approach these two questions. Okay, so we talked about threshold signatures, the theory, and we talked about single party Schnorr signatures, and sort of how you might approach these problems. So at this point, you might be saying like, okay, but why are these schemes useful at all? Why should I care about this? And in designing Frost, the motivation really came from the Zcash setting. So what we wanted in Zcash is we wanted a multi-party signature scheme that would not leak the number of parties. And so what we wanted is a signature scheme that would be essentially indistinguishable on chain, and you wouldn't be able to track signatures or you wouldn't be able to track keys by the number of parties that they represented. So a counterexample is, for example, if you had a signature that was associated with a public key that always represented 21 parties, that would be a privacy leak because you could sort of track it throughout time and associate transactions with each other. So in the Zcash setting, Frost was of interest because of the privacy properties it provided on chain. But yeah, so in the Zcash setting, we wanted a threshold Schnorr signature scheme, but the work that existed at that time was undesirable because of its efficiency trade-offs. So the work that existed at that time is there was a 5-round scheme proposed by Stinson and Strobel, and then there was a 3-round multi-signature scheme that was proposed, and basically you could take this and translate it to the threshold setting. But yeah, basically there was a 5-round and 3-round schemes respectively. And so the main driving research question we had was essentially, could we design a round efficient threshold Schnorr signature? So what we wanted to do is we wanted to design something that had fewer rounds than 5 and 3. And so we did have our first attempt at this, and our first attempt ended up being insecure. So let me walk you through what that first attempt was. So the first attempt required each party to generate a nonce and its commitment similar to as in Schnorr signatures. And then each party would publish their commitment to all their parties, and then they would receive commitments from all other parties. Okay, so essentially they generate a nonce and commitment exactly the same as in single party Schnorr. Then the group commitment was just the product of all the commitments published by all of the parties. And then the challenge was derived in exactly the same way as Schnorr signatures. And then the response looks very similar to the response for Schnorr signatures, but here we have this lambda, and this is essentially what allows for the Shamir secret sharing. So I'll talk about this actually in a later slide, but you can just think that the secret key is Shamir secret shared, and then the lambda I is what allows everything to be reconstructed. So basically what combine here allows for is you have a combine function which takes all of the responses and sums them, and then this produces a single response Z. And then this signature, when you publish the group commitment and then the response, is verifiable under the single party Schnorr verification algorithm. So the scheme is correct in that basically you take all the responses, sum them, and then when you create the group commitment in this way, it is verifiable under the same verification algorithm as single party Schnorr. But the security of the scheme comes with a caveat in that it is secure only in a sequential setting. So if the signer were to issue one signature at a time, the scheme would be secure. But if the adversary could open many signing rounds in parallel, the scheme is insecure. And so essentially the reason why the scheme is insecure in the concurrent setting is due to this attack called the ROS attack. And I'll just refer to different papers that describe the problem and the attack. But it really comes down to the fact, like I said, that the adversary can open many signing sessions at the beginning and receive commitments for honest parties before it chooses its own commitment. So it comes down to the fact that it's an adaptive attack where the adversary can see many, many first round sessions before determining its own output. And it is a forgery attack. And it's not just multi-signatures and threshold signatures that are affected. This problem also pops up in the setting of blind signatures as well. So any kind of like linear signature scheme, you have to consider ROS attacks. Okay, so I'll show you really briefly how this attack comes up in the first attempt that I showed you. Basically, like I said, a participant would publish many of its first round commitments and then receive these commitments from all the other parties. And then the honest party would generate the commitment, the challenge, and the response. And essentially, the challenge to the adversary is given many signing sessions, it should be able to find some challenge which sums to challenges issued from honest signing sessions, such that the relation for the response holds. So basically, it comes down to the fact that the adversary can find some C star, which is equal to the sum of challenges from honest signing sessions. And then they can produce a forgery simply by combining responses from these different sessions. Yeah, and so that's why the ROS attack really pops up for linear signature schemes in particular. Okay, but again, like I said, this requires the adversary to adaptively choose its contributions after seeing the victims. So yeah, so the reason why I think it's important to point out this attack is because many schemes in the literature proposed this insecure scheme that I just showed you. And it wasn't for a while that it was pointed out, like, actually, these are insecure. And many of these schemes had proofs of security, and the proofs of security were broken in very subtle ways. So yeah, so like this actually happened. These schemes were proposed, and they were insecure. And yeah, also the MuSig2 scheme, a prior version of it, also proposed this insecure scheme, as well as the first version of Frost that we worked on. So, so yeah, so many schemes in literature have made this mistake, us included. And there is one way to fix this mistake, but it requires 3 rounds. So it requires the adversary to commit to its contributions before publishing them in the clear. And this is MuSig2 after the fix, but there's also similar techniques used in other schemes in the literature. So it begins in the same way as the scheme that I showed you before, but then each party generates a commitment, which is a hash of the big RI and the message and the signing set. And then each party publishes this commitment to their commitment, essentially. And then they send the commitments in the clear. So here, this forces each party to really commit to their big RIs before revealing them. So you can think of this as a commit reveal protocol. And then again, the group commitment is derived in the same way as I showed you, and the challenge and the response. So here we just add an extra round in front, which commits to everything, and this prevents the ROS attack attack that I showed you. Okay, but this requires 3 online rounds. And so, yeah, so really for Frost and MuSig2, we wanted to do better. So we said, okay, you can have this commit reveal type of scheme, but we wanted to see if we can do better. And so this is where we came up with the innovation that resulted in Frost and MuSig2. And this second solution was to essentially tweak the signature in such a way that even if the adversary were able to perform an adaptive attack, this adaptive attack would not be useful in the end. And it's by essentially using this tweak. So I'm going to show you this technique for Frost, and then Jonas is going to show you this technique for MuSig2. So first, though, I'm going to walk you through how the secret key is actually generated. I showed you this kind of implicitly before, but I'm just going to call it out really briefly now. So what I said before is we use Shamir secret sharing to generate the key. And the way that we do that is we essentially define a polynomial where the constant term is the secret key, and all of the coefficients of this polynomial are generated at random. So here we have this polynomial f, and this constant term is the secret key, and then all of the coefficients, the a's, are sampled uniformly at random. And then the share, the skj, is just the polynomial evaluated at that point for that particular party. So each party is assigned an identifier. So for example, for party J, their secret key share is just f of J. And then the public key is just the generator raised to the secret key. So here I'm describing Shamir secret sharing, and this is just under the hood what's going on. And so a trusted dealer would perform this and send key shares to all parties. And then what I showed you before, this lambda I, what is going on is you're able to essentially recover any point on the polynomial using t points. So so essentially what you do is you're doing polynomial interpolation, and you're interpolating the polynomial to some particular point. And this lambda I is just allowing to interpolate the polynomial using t points to the constant term. So when you see summation of ski lambda I, you can think of this as interpolating to the secret key. And when I told you about distributed key generation prior in the talk, really what you're doing is you're doing that same Shamir secret sharing operation, but where that Shamir secret sharing, there's no trusted dealer. So you're essentially doing an MPC protocol to generate secret keys with the same Shamir secret sharing structure, but in a way that no party knows either SK or any other party's SKIs. So I just want to throw that out there just so we have in the back of our heads that you can do this operation in a distributed way as well. Yeah. Okay, so now I'm going to talk to you about Frost. So as I said before, Frost stands for the Flexible Round Optimized Schnorr Threshold Signature Scheme. And this work was published by myself and Ian Goldberg in 2020. And in this work, we give a couple different schemes. The first is what came to be known as PEDPOP, which is a distributed key generation protocol. And I'm just going to mention that we introduced that in this work, and we're not going to talk anymore about it. And then additionally, we give this 2-round threshold signing scheme that is concurrently secure. And yeah, like I said, it was designed to solve the needs in Zcash. And now we will look at the scheme in more detail. So for Frost, the way the scheme begins is each party generates their nonces, but here instead of generating just one nonce, they generate 2. So here they generate both RI and SI. and then they generate two commitments to these nonces. So we have big Ri and big Si. And then each party just outputs both of these commitments in the clear. So here we don't need a commitment round, we just output both commitments directly, and then each party receives both commitments directly as well. And then differently from the schemes that we saw prior, each party will then hash the commitments received from all other parties, as well as the identifier. So essentially what we're doing is we're sort of hashing the transcript from the first round. So we're hashing the public key, the message, and then all of the signing parties as well as their commitments. And then the group commitment also differs from the schemes that we saw before, where here we're actually taking the product of big I and big Ri and big Si, but here where Si is raised to this, what we essentially call a tweak. So you can think of this A value as a tweak. The challenge is derived in exactly the same way as in regular Schnorr. And then the response does something similar as, or it departs from what we saw before. So the response takes both of the nonces, the Ri and Si, and then it adds in this tweak value with respect to Si. And then here we see again this challenge multiplied by the SKI and lambda I. So this is what is allowing for Shamir secret sharing under the hood. And combining and verification is identical to what we saw before. So here we sum all of the responses, and then verification is again identical to what we saw for Shamir secret sharing. So with the summation, what we're getting is we're getting interpolation of the secret key shares in such a way that it's valid under the joint public key. Okay. So yeah, so this is Frost, and this can be performed in 2 rounds of signing. But what's also really nice is that the first round can actually be pre-processed. So the first round is agnostic to the signing set, as well as the message that needs to be signed. So all parties can essentially generate their commitments and then publish them somewhere. And then later, some coordinating party can decide who they want to sign and what message needs to be signed. And I just want to point out that this pre-processing step is actually being used in practice. So it is quite useful that this first round of signing is agnostic to the message and signing set. And it makes it something appealing about both Frost and MuSig2. So this is Frost. This technique of generating 2 nonces and using this tweak is also used by MuSig2. So this kind of innovation about tweaking the signature is the main technical innovation, and it is also shared by MuSig2. And Jonas will show you how that is done in MuSig2 in a little bit. Okay. So you might wonder, so I said essentially Frost is correct. And I just want to sort of point out again that the correctness of Frost comes down to Shamir secret sharing. So as I said, essentially if you take the summation of t points on a polynomial of degree t minus 1, you can interpolate to any other point on the polynomial. So this lambda I is what is allowing for Lagrange interpolation to the constant term of this polynomial. So I just sort of want to point out again why Frost is correct and why signatures are valid under the single party public key. Okay, so I want to sort of walk you through really briefly about how you can prove security of this scheme. So just as a reminder, how we prove security for cryptographic protocols is the main goal when we prove security is to show essentially that if we believe a mathematical assumption is hard, then the scheme that we're trying to prove security of is also, then it's also hard to break the security of a scheme. So yeah, so the contrapositive of this is we say if the adversary can break the security of some scheme, then it is possible to efficiently solve a hard mathematical problem. And yeah, so essentially this is sort of how we prove cryptographic schemes to be secure. And that is how we prove the security of Frost. So we show that if there exists an adversary that can break the security of Frost, then we can use that adversary by some reduction to solve what we call this AOMDL problem. And what this AOMDL problem is it says, given L+1 discrete log challenges, it is hard to output L+1 solutions with only L queries to a discrete log solution oracle. Yep, so basically it's an interactive assumption. So we say, given these challenges, if I can query for solution only on a limited number of them, it should be hard to output a solution for all of them. So yeah, so basically we have this AOMDL challenger. It gives the challenges. Then the AOMDL adversary is able to interact with the challenger by querying this DL oracle. And at the end, it's required to output the solutions to the challenges. Okay, so yeah, so basically to prove the security of both Frost and MuSig2, we show this reduction. So we say, given a successful unforgeability adversary for Frost and MuSig2, we can then define a reduction which uses this adversary in order to solve the AOMDL problem. Okay, so then the contrapositive holds. So basically we say, yeah, so if this is true, then if AOMDL is hard, then this kind of adversary is infeasible. Okay, so yeah, so this is basically how we show the security at a very high level. And yeah, so I just want to sort of point out that, so I showed Frost and I've been talking a lot about MuSig2, but other schemes have emerged in the literature and they sort of fall into this 3 and 2 round category that I showed you. So yeah, so just kind of briefly wrapping up. So Frost is now available as an informational RFC within the IETF, and it's also been specified for use within Zcash. And we are currently working on a NIST submission for Frost. So there's a bunch of us across different organizations, and so we're working to standardize Frost within NIST. And Frost is used in practice throughout the ecosystem. So we're very happy that Frost has already been deployed and is in use. And so yeah, both Frost and MuSig2 have sort of inspired a lot of follow-up work. So since the original Frost paper, there have been improved proofs of security for Frost. There's been work showing how to make Frost robust. So essentially, so that a signature is always output after performing a round of signing. And then we've shown new constructions for threshold key generation. And then there's also been threshold signature schemes with weaker security assumptions. So essentially showing how to get threshold schemes without using interactive assumptions, as well as post-quantum, essentially lattice-based MuSig2 and Frost. And all right, so with that, I'm going to hand this off to Jonas, who's going to be talking about MuSig2. All right, thanks very much.
Hello, I am going to talk about MuSig2, in particular some of the practical aspects, but before doing that I would like to take the time and talk a little bit about the context and history of MuSig2. And a natural starting point for that is the publication of the original MuSig paper, which I call MuSig1 here to better distinguish it from MuSig2. It was published on ePrint in January 2018, and it inspired MuSig2, which was published on ePrint in July 2021 and appeared at Eurocrypt 2024. And it also inspired the taproot soft fork for Bitcoin, which was published on the Bitcoin mailing list, at least the initial ideas, in January 2018. So MuSig2 is simple Schnorr multi-signatures with applications to Bitcoin. More specifically, it's the first Schnorr signature compatible multi-signature scheme with non-interactive public key aggregation. So in order to compute an aggregate public key, PK tilde, you use a key aggregation algorithm that takes the individual signer's public keys as input and outputs an aggregate public key. And then the signing protocol is very similar to what Chelsea showed earlier in one of her slides. It consists of 3 communication rounds. The first round exchanges the commitments. In the second round the nonces are exchanged, and then the signers output partial signatures Z that are going to be aggregated. Note that because this is a multi-signature, there is no threshold T here. All N signers need to cooperate to produce a signature. And one of the main insights of this work was that Bitcoin moving to Schnorr signatures would definitely help deploying compact multi-signatures, because it would allow using MuSig for multi-signatures, and at the time Bitcoin only supported ECDSA. Why would you want to use MuSig on Bitcoin? Bitcoin has always supported what can be called trivial multi-signatures, where the public key is just the list of the individual public keys and the signature is just the list of individual signatures. This has a couple of problems, one of them being privacy, because if we have a transaction with an output containing a trivial multi-signature, then that's easy to see for a blockchain observer. In this case, we have 3 signers involved in that trivial multi-signature. But it gets worse. If this group of signers makes a transaction to some recipient, which is typically using a single signature scheme, they create a transaction with 2 outputs, one going to the recipient, the other one going back to the group of signers as change. Now, for a blockchain observer, it's very easy to see which one of the 2 outputs are the change outputs, because that will be the one with a trivial multi-signature. And this is terrible, because a blockchain observer can now follow the transaction of this wallet by just trying to find the change output. If the signers would not, if this would not be a trivial multi-signature, but instead just a single signer, then we don't have such a problem, because then it would not be easily distinguishable which output is change and which output is the recipient. Now, using MuSig allows for improved privacy, because the public keys in MuSig are indistinguishable from regular Schnorr public keys, and signatures are indistinguishable from regular Schnorr signatures. And for the same reason, this also allows saving transaction fees. Now, Bitcoin only supported ECDSA at the time of the publication of MuSig, and what enabled Schnorr signatures on Bitcoin eventually was the Taproot soft fork upgrade. Taproot consists of a specification for Schnorr signatures, that is Bitcoin Improvement Proposal 340. Signatures are 64 bytes, and they are defined over curve SecP256K1, same curve as used for ECDSA. Public keys are 32 bytes, by the way. And perhaps surprisingly, the verification code fits on a t-shirt. So this t-shirt code contains all elliptic curve operations. The only external dependency is SHA-256. And BIP 340 was designed to support multi- and threshold signatures. The main part of Taproot are the actual Taproot spending rules defined in BIP 341. And a crucial ingredient for that are taproot commitments. This is a commitment scheme that consists of a commit algorithm that takes a message and a group element and outputs a group element. So far, so good, but the key feature is that knowledge of the discrete logarithm x of the input group element allows computing the discrete logarithm of the output group element. So we have an additional algorithm that I call taptweak here that takes a message and a scalar and outputs a scalar. And if we want to compute the discrete logarithm of some commitment, then we can use the taptweak algorithm. Note that this requires knowledge of the discrete logarithm of the input group element, x here. And this allows us to define the taproot spending rules. Coins contain a taproot commitment, and they can be spent in two different ways. Either through a key spend, which requires a Schnorr signature using the commitment as the public key. And the secret key is computed via taptweak. Or the coin can be spent via a script spend, which requires opening the commitment to M, which is interpreted as a tree of alternative spending conditions, and then satisfying one of the conditions. Now, what makes taproot really useful in practice is what we call the taproot assumption that was already stated in the original post to the Bitcoin mailing list. And it says, it is almost always the case that interesting scripts have a logical top-level branch which allows satisfaction of the contract with nothing other than a signature by all parties. So in other words, if all participants of some contract agree, they can use the key spend path with a MuSig multi-signature. And this does not require revealing the alternative spending conditions and is indistinguishable from a normal single signature transaction. So with MuSig2 being published and taproot being proposed, we worked on an implementation. But we were quite annoyed by these 3 communication rounds because we had to design an API that keeps state securely and is easy to use and hard to misuse. But luckily, Tim Ruffing refused to believe that a 2 communication round scheme is impossible, and he actually found a solution which seemed rather improbable at the time because quite a few people had already looked at this and did not find a solution. Remember, this was before Frost was published. So we teamed up with Yannick Serin, who is an absolute master in signature cryptography and writing those proofs, and we wrote the MuSig2 paper together. So MuSig2 is simple 2-round Schnorr multi-signatures. Key aggregation works exactly the same as in MuSig1. And the signing scheme works very similar to Frost. We have 2 communication rounds, but the main difference, essentially the only real difference to Frost, is that in order to compute a partial signature Z, you do not multiply the challenge Z and the signing key with a Lagrange coefficient, but you multiply it with a key aggregation coefficient, alpha. Alpha also appears in the key aggregation algorithm, which is actually pretty simple. It is just the product of the individual public keys after taking them to the power of their key aggregation coefficient. And the key aggregation coefficient is pretty simple as well. It is just the hash of all public keys and this individual public key. And similar to Frost, the first round can be batched and is agnostic to message and signing set. So you can view MuSig2 even as a non-interactive signature scheme with preprocessing, where the preprocessing step is exchanging the nonces. So MuSig2 in practice. Taproot was locked in June 2021 and it activated in November 2021. So we worked on BIP MuSig2, which is a specification that is compatible with the Schnorr signatures that were introduced by Taproot. It includes a Python reference implementation and exhaustive test vectors that test all kinds of failure conditions that we can test. It supports Taproot commitments and a few other features that are not part of the MuSig2 paper. So based on that, people wrote specifications in particular for defining how wallets would use MuSig2, descriptors, partially signed Bitcoin transactions, etc. And we wrote an implementation for libsec P256K1, which is the crypto library used by Bitcoin Core. And based on those, people wrote wallet applications and layer 2s. The first draft version of BIP MuSig was published in May 2022, and the final version 1 was released in March 2023. And the libsec implementation was merged just recently in October. And now, a natural question to ask is, why did it take almost 3.5 years from Taproot login to having an implementation in libsec P256K1? And can we accelerate the development timeline for similar projects in the future? First, the BIP development and implementation already occurred in parallel, so this was not a purely sequential process as this previous diagram would have suggested, but there were several factors that slowed down the timeline. In particular, you need to get feedback from experts, but experts tend to be busy with other things. Also, you need to get feedback from potential users, but implementations take time and usually they don't happen until BIP or library is finalized. And also there was some sort of limited urgency because on average the fee pressure on the Bitcoin network was quite low. Maximizing the clarity and understandability of the BIP takes a lot of time. This includes building the exhaustive test framework and also validating features of the BIP that are not covered by the MuSig2 security proof. And moreover, designing misuse-resistant APIs is a laborious process, and I'm going to give examples now for why this is important in practice. So first, we have this difference between theory and practice. In theory, we have a key generation algorithm. This is the one from the MuSig2 paper. It looks complicated, but it's very simple. You draw a uniformly random secret key X, and then you compute a public key capital X, and you return this key pair. But in practice, in Bitcoin, people do something different to obtain keys. Namely, they have a master key and then they derive child keys using BIP32. And those child keys are used as signing keys. And because they are derived from a master key, they are related. And this use of MuSig2 with related keys in practice actually led to an attack against the latest version of BIP MuSig at the time. So using the key generation algorithm as specified in the paper is still secure. Security proof covers it, but the security proof does not cover the related keys that appear in practice. So this attack requires specific circumstances and an active exploitation, which is why I would rate the security impact as moderate. And fix is straightforward, and it was fixed before version 1.0 of BIP MuSig2 was published. But what is particularly interesting is that the discovery of this was entirely incidental. We were working on a different scheme, namely nested MuSig, and we were trying to prove one of our candidate schemes secure, and we noticed that this candidate scheme had a problem, and then we realized that this same problem would also apply to using MuSig2 with related keys. So our key learning from this is that security proofs should cover practical use as much as possible, and in particular, they should cover related keys. Now we get into an example for why misuse-resistant API design is important. This is a screenshot of a comment on a pull request related to BIP MuSig2. And I'm just going to read the highlighted part. The name session ID somehow made me think it had to be shared between everyone in the signing session. So we define session ID in the MuSig2 BIP, and we documented it correctly. It needs to be uniformly random and kept secret. But this name alone, session ID, made this user think that it can be shared between everyone in the signing session, and this is a very wrong idea. So after reading this, we renamed session ID to session secure randomness, because this is the essential randomness that is used to derive nonces. So in hindsight, this seems to be like an obvious mistake by us, but we had to give many names to things in the MuSig2 BIP, and this was simply an oversight. Here's another example. So this is from our implementation in libsec P256K1, where we have this secret nonce struct, and we mention multiple times in the documentation that this structure is never to be copied. Don't copy this thing. So someone was reaching out to me, and they were explaining their use of the libsec P MuSig API to me, and then I replied to them, hey, you mentioned you're planning to store the nonces in the wallet file. What happens if someone restores an old wallet or wildly copies the wallet file around? Wouldn't that mean that the user may reuse their nonce? And yes, it turned out that this could have resulted in nonce reuse. And nonce reuse in MuSig2 is just as bad as nonce reuse in ordinary Schnorr signatures. So the developer in general was aware of the risks with nonce reuse, but they failed to consider that the sort of copying they were doing would lead to nonce reuse, because generating a new random nonce each time should be good enough, is what they said, but actually that is not good enough. So what can we do about this? And this really is an open question, because I don't have a good answer to that. Ideally, we would design crypto schemes that don't have such problems, but that is just not always possible. Applications of MuSig2. So there are a bunch of applications in production. One of them is a wallet with a third-party programmable cosigner that is operated by BitGo. It instantiates a 2 out of 3 spending policy using MuSig2 and the taproot tree. And I should note that it is important, it is impossible for us to observe the actual amount of adoption of MuSig2 on the blockchain, because it is indistinguishable from single signature use. Another big application that is currently in production are swaps between the Lightning Network and on-chain Bitcoin. For example, there's Lightning Labs Loop and also Bolts. And they typically use a 2 of 2. And there are in development applications, such as using MuSig for MuSig2, I should say, for Lightning Network channels themselves. That would be a 2 of 2. And there's a pull request to the Bitcoin Core wallet to enable MuSig2, and that would allow very flexible spending policies. And there's more. In particular, there are these applications that don't have the usual motivation of just saving fees or providing more privacy. For example, there's the covenantless ARC-Clark protocol, and they want to use MuSig to construct super massive multisig for ARC's transaction tree. So they're talking about groups of signers that have 10,000 members. And this would be prohibitively expensive with trivial multi-signatures. And another advanced application is Mercury Layer. They refresh MuSig2 secret keys to transfer coins without a transaction using a semi-trusted server. And a key refresh is impossible with traditional multisig. So now I'm going to quickly touch on some of the most requested MuSig2 Frost extensions by practitioners. So if you're interested in that, feel free to reach out to me. So one possible extension is blind Frost in MuSig2 signing, where the signer does not learn the message they are signing, and in some cases not even learns the public key they're signing under. And sometimes it's enough that the signing scheme is purely used in the sequential setting and not in the concurrent signing setting. Then there's this notion of nested, also known as recursive Frost in MuSig, where each of the aggregated keys can itself be a MuSig2 aggregate or Frost key. This is, for example, used to build something that is sometimes called multi-sig lightning. Stateless MuSig2 Frost would be really, really nice because it would get rid of this entire class of nonce reuse issues. And this actually exists in contrast to the other things on this slide, but is very complex and or it requires an honest majority. So as far as I am aware, no one has implemented that so far. It would be interesting to combine MuSig2 Frost with silent payments. Silent payments is a scheme that allows for reusable addresses in Bitcoin without having the usual negative privacy impact on the blockchain. And a highly requested extension is dynamic membership MuSig2 and Frost, where you can change the number of signers, the threshold T, or the members of the signing group without a Bitcoin transaction. So this is the final slide. Some of our learnings of this multi-year saga. Our research turned out to be valuable because it is solving real-world problems. But for that to happen in general, there needs to be effective communication between practitioners and researchers. Approach problems with your unique perspective. For example, the feedback we get that is out of the box is usually the most valuable. Of course, sometimes it can also be totally misguided, but that is typically worth it. Also, if you are fixated on a problem, then persist in finding solutions. We've seen an example of that, the discovery of 2 communication round signing schemes. And maybe you don't find a solution, but at least you could learn something during the process. Cryptographic schemes should take practical concerns into account. We've seen examples of those practical concerns: statefulness, related keys, misuse resistance, communication rounds, and more. We believe that our active effort in writing specifications and writing implementations accelerated the real-world impact of this research. Active effort does not need to go as far as writing specifications, but it can start by approaching practitioners with your idea, trying to convince them it's a good idea, or learn why they think it's not a good idea, and learn about what they actually need. So finally, I would like to give a special thanks to our co-authors, Ian, Tim, and Yannick. And also thanks to everyone who helped putting this research into practice, including researchers, implementers, and reviewers. Thank you.